Today I will discuss the solar thermal collectors. The content of this lecture is the concentrating collector. In the previous lecture I already described the non-concentrating collector. Today I will discuss the different types of concentrating collectors. The concentrating collectors, unlike the solar cells, which use the light to produce electricity, concentrating solar power systems generate electricity with heat. These technologies can be used to generate the electricity for a variety of applications, ranging from remote power systems as small as a few kilowatts up to the grid-connected applications of 200 to 350 megawatts or more. A concentrating solar power system that produces 350 megawatt of electricity displaces the energy equivalent of 2.3 million barrels of oil. Many designs have been considered for concentrating collectors. Concentrators can be reflectors or refractors, can be cylindrical or parabolic, and can be continuous or segmented. Receivers can be convex, flat, cylindrical, or concave, and can be covered with the glazing or uncovered. Concentration ratios such that the ratio of the aperture to the absorber areas can vary over the several orders of magnitude, from as low as unity to high values of the order of 10,000. Increased ratios means the increased temperatures at which energy can be delivered, but consequently these collectors have increased requirements for precision in optical quality and positioning of the optical system. In the concentrating collectors, solar energy is optically concentrated before being transferred into the heat. The concentration can be obtained by reflection or refraction of the solar radiation by the use of the mirror or the lens. The reflected or the refracted light is concentrated in a focal zone, thus increasing the energy flux in the receiving target. Concentrating collectors can also be classified into the non-imaging and the imaging depending upon whether the image of the sun is focused at the receiver or not. The receiver absorbs and converts the sunlight into the heat. The heat is then transported to a steam generator or the engine where it is converted into the electricity. Because of the apparent movement of the sun across the sky, the conventional concentrating collectors must follow the sun's daily motion. There are two methods by which the sun's motion can be readily tracked. One is the alt-azimuth method, which requires the tracking device to turn in both altitude and azimuth, such that when performed properly, this method enables the concentrator to follow the sun exactly. Paraboloidal solar collectors are generally used in this system. Another is the one-axis tracking method, in which the collector tracks the sun in only one direction, either from east to west or from the north to south. The parabolic trough collectors (PTC) generally used in this system. These systems require the continuous and accurate adjustment to compensate for the changes in the sun's orientation. There are four types of concentrating solar power systems are there, which are available in the market. That is the parabolic trough collector, linear Fresnel reflector, parabolic dish, and the central receiver. Now come to the parabolic trap collectors. In order to deliver the high temperatures with good efficiency, a high performance solar collector is required. The parabolic trap collectors can effectively produce the heat at the temperatures between the 50 and the 400 degrees centigrade as well. The systems with the light structures and the low-cost technology for process heat applications up to the 400 degrees centigrade could be obtained with parabolic trap collectors. The parabolic trap collectors are the most mature solar technology now. The biggest application of this type of system is the Southern California power plants known as the Solar Electric Generating Systems (CEGS), which have a total installed capacity of 354 megawatt. Now the construction of the parabolic trap collectors. PTCs are made by bending a sheet of reflective material into a linear parabolic shape. A metal black tube covered with a fluid carrying glass tube to reduce the heat losses is placed along the focal line of the receiver. The size of the tube and therefore the concentration ratio is determined by the size of the reflected sun image and the manufacturing tolerances of the trap. The shape of the receiver is typically plated with the selective coating that has a high absorptance for the solar radiation but a low emittance for thermal radiation loss. A glass covered tube is usually placed around the receiver tube to reduce the convective heat loss from the receiver, thereby further reducing the heat loss coefficient. A disadvantage of the glass covered tube is that the reflected light from the concentrator must pass through the glass to reach the absorber, adding a transmittance loss of about 0.9 when the glass is clean. The glass envelope usually has an anti-reflective coating to improve the transmission. One way to further reduce the convective heat loss from the receiver tube and thereby increase the performance of the collector, particularly for high temperature applications, is to evacuate the space between the glass covered tube and the receiver. The energy from the sun sent to the tube heats well, flowing through the tube, and the heat energy is then used to generate the electricity in a conventional steam generator. Many traps placed in the parallel rows are called a collector field. The traps in the field are all aligned along a north-south axis so they can track the sun from east to west during the day, ensuring that the sun is continuously focused on the receiver pipes. Individual trap systems currently can generate about the 80 megawatt of electricity. The trap designs can incorporate thermal storage, setting aside the heat transfer fluid in its hot phase, allowing for electricity generation the several hours into the evening. Currently, all the parabolic trap plants are the hybrids, meaning they use the fossil fuels to supplement the solar output during the periods of low solar radiation. In order to achieve the cost effectiveness in the mass production, not only the collector structure must feature a high stiffness to weight ratio so as to keep the material content to a minimum, but also the collector structure must be amenable to low labor manufacturing process. A number of structural concepts have been proposed, such as the steel framework structures with central torque tubes, or the double V trusses, or the fiberglass. A recent development in this type of collector is the design and manufacture of the Eurotrap, a new PTC, in which an advanced lightweight structure is used to achieve the cost-efficient solar power generation. Based on the environmental test data up to date, mirror glass appears to be the preferred mirror material, although the self-adhesive reflective materials with the 5 to 7 years life exist in the market. A tracking mechanism must be reliable and able to follow the sun with a certain degree of accuracy, return the collector to its original position at the end of the day or during the night, and also track the during periods of the intermittent cloud cover. Additionally, the tracking mechanisms are used for the protection of collectors such that they turn the collector out of focus to protect it from the hazardous environmental and working conditions like wind gust, overheating, and failure of the thermal fluid flow mechanism. The required accuracy of the tracking mechanism depends on the collector acceptance angle. Now come to the second type of concentrating solar thermal collector, that is the linear Fresnel reflector. The linear Fresnel reflector technology received its name from the Fresnel lens, which has multiple refracting planes designed to improve the concentration of the light coming from many different angles onto a single point or line. This lens was developed by the Augustin Jean Fresnel in the 18th century and allows a substantial reduction in the thickness, volume, and weight of the lens, but also reduces the quality of imaging. The linear Fresnel reflector technology relies on an array of linear mirror strips which concentrate light onto a fixed receiver mounted on a linear tower. The LFR field can be imagined as a broken up parabolic trough reflector, but unlike the parabolic troughs, it does not have to be of parabolic shape. Large absorbers can be constructed and the absorber does not have to move. A representation of an element of an LFR collector field is shown in the figure. A linear Fresnel reflector's design is based on a principle between the power tower and the parabolic trough concentrator system. It is similar to parabolic trough system but contains fixed receiver pipe while the mirrors track. The trough shape is split into the multiple mirror facets. This mirror based the system uses the same principle as a Fresnel lens uses for flat plane mirrors that track the sun to reflect light onto a tube. An additional secondary mirror is used in some systems shown in the figure behind the focal plane, which directs the sunlight into the absorber pipe. The linear Fresnel reflector system shown in the figure uses the long rows of the flat or slightly curved mirrors to reflect the sunlight onto a downward facing raised linear collector containing two stainless steel absorber tubes. The collector in this system is a fixed absorber tube located at the common focal line of the mirror reflectors, equipped with single or dual axis tracker to minimize the amount of sun energy collected throughout the day. A secondary concentrator is used to reflect the rays within the accepting angle. The Fresnel reflectors concentrate beam radiation to a stationary receiver. The receiver consists of two stainless steel absorber tubes. Each receiver has a secondary CPC reflector that directs beam radiation onto the absorber tube. The entire optical system is enclosed in a sealed glazed casing. The absorber tube contains the transfer fluid, which is heated to create the superheated steam that runs a turbine to produce electricity. New systems are designed that heat water to produce steam at 285 degrees centigrade in the absorber tubes, which will be directly used to drive a turbine to generate electricity instead of using a heat exchanger to produce the steam from the other high temperature fluids. The system has a limited temperature rising performance and is less efficient than other CSP systems, but its simple design of ground mounted mirrors makes it cheaper than the other solar trap systems. This system is ideal for small standalone systems in the remote areas. Because of the fixed absorber and the flat tracking mirrors, the system is structurally simpler and less expensive than the other CSP systems. The linear Fresnel systems occupy less space than the linear trap and the power tower systems, and they can be combined with the fossil fuel backup for the power generation during the night or the cloudy days. Compared with the parabolic trap technology, the energy yield per unit area is much smaller, yet the simple structure of the Fresnel collector and the possibility of using the space beneath the collector means that there is an important cost lowering potential that can be exploited. The total cost of the system is comparatively low. However, due to the system's low concentration ratio, the operational temperature stays low, resulting in low system efficiency as well. The disadvantage of the linear Fresnel reflectors having only one receiver is that it is difficult to change the receiver's direction for a large size of the field required in a multi-megawatt power generating system. But this problem is solved in compact linear Fresnel reflector system, which uses two parallel receivers for each row of the reflectors. If the receivers in the CLFR are close enough, then the individual reflectors can direct reflected solar radiation to at least two receivers, allowing them to be more densely packed arrays and have the lower absorber height. The receiver tube in CLFR systems are placed at the focal point of a series mirrors. The additional set of mirrors are also placed across the top of the tubes in order to capture and refocus any sunlight that does not directly hit the tubes. This configuration assures that all the available light is used. Depending on the position of the sun, the reflectors can be alternated at different receivers to improve the optical efficiency. Compared to the linear Fresnel reflector system, the CLFR system can generate a large amount of heat and is the cost effective in a small land area. The CFLR systems are scalable to the power plant needs and can be applied as standalone plants as well as a booster in the industrial applications. Now come to the parabolic dish reflector. The dish reflectors use the dish-shaped parabolic mirrors as the reflectors to concentrate and focus the sun's rays onto the receiver, which is mounted above the dish at the dish center. A dish or the engine system is a standalone unit composed primarily of a collector, a receiver, and an engine. It works by the collecting and the concentrating the sun's energy with a dish-shaped surface onto a receiver that absorbs the radiant solar energy, converting it into the thermal energy in a circulating fluid and transfer it to the engine. A parabolic dish reflector shown schematically in the figure, which is a point focus collector that tracks the sun in two axes, concentrating solar energy onto a receiver located at the focal point of the dish. The dish structure must track fully the sun to reflect the beam into the thermal receiver. The engine then converts that energy to the heat. The heat is then converted to the mechanical power in a manner similar to the conventional engines. By compressing the working fluid when it is cold, heating the compressed working fluid, and then expanding it through a turbine or with a piston to produce the mechanical power. An electric generator or the alternator converts this mechanical power into the electrical power. These or the engine systems use the dual axis collectors to track the sun. The ideal concentrator shape is parabolic, created either by a single reflective surface or the multiple reflectors or the facets. Many options exist for the receiver and the engine type, including the Stirling cycle, microturbine, and the concentrating photovoltaic modules. Each dish produces 5 to 50 kilowatt of the electricity and can be used independently or linked together to increase the generating capacity. A 250 kilowatt plant composed of 10-25 kilowatt dish or engine systems requires less than an acre of land. The advantage of the parabolic dish reflector, because they are always pointing at the sun, they are the most efficient of the all collector systems. Secondly, they typically have the concentration ratio in the range of 600 to 2000 and thus are highly efficient as the thermal energy absorption and the power conversion systems. They have the modular collector and the receiver units that can either function independently or as a part of a larger system of the dishes. Now the last type of the concentrating solar thermal collector is the central receiver or the heliostat field collector. For extremely high inputs of the radiant energy, the central receivers or the power towers use the thousands of individual sun tracking mirrors, which are called the heliostats, using the alt-azimuth mounts to reflect their incident direct solar radiation onto a receiver located on the top of the alt tower. By using the slightly concave mirror segments on the heliostats, large amounts of thermal energy can be directed into the cavity of a steam generator to produce the steam at the high temperature and pressures. In the figure here, we can see the heliostats. The sun rays are falling down on the heliostats. Then the receiver at the top of the tower collect this and the large amount of thermal energy can be directed into the cavity of a steam generator to produce the steam at the high temperature and the pressure. The concentrated heat energy absorbed by the receiver is transferred to a circulating fluid that can be stored and later used to produce the power. The salt's heat energy is then used to make the steam to generate the electricity in a conventional steam generator located at the foot of the tower, which is shown in the figure. The molten salt storage system retains the heat efficiency so it can be stored for the hours or even the days before being used to generate electricity. Therefore, a central receiver system is composed of 5 main components. One is the heliostats, the mirrors. Another is the receiver, which are at the top of the tower, the heat transport and the exchange, thermal storage and controls. The molten salt at the 554 degree Fahrenheit is pumped from a cold storage tank through the receiver, where it is heated to about 1050 Fahrenheit. The heated salt then moves onto the hot storage tank. When the power is needed from the plant, the hot salt is pumped to a generator that produces the steam. The steam activates a turbine or the generator system that creates the electricity. From the steam generator, the salt is returned to the cold storage tank, where it's stored and can be eventually reheated in the receiver. By using the thermal storage power, the tower plants can potentially operate for the 65% of the year without the need for a backup fuel source. Without energy storage, solar technologies like these are limited to annual capacity factors near 25%. The power tower's ability to operate for extended periods of time on the stored solar energy separates it from other renewable energy technologies. Each heliostat at a central receiver facility has from 50 to 150 meters square of the reflective surface. The heliostats collect and concentrate sunlight onto the receiver, which absorbs the concentrated sunlight, transferring its energy to a heat transfer fluid. The heat transport system, which consists primarily of pipes, pumps, and the valves, directs the transfer fluid in a closed loop between the receiver, storage, and the power conversion. A thermal storage system typically stores the collected energy as sensible heat for the later delivery to the power conversion system. The storage system also decouples the collection of solar energy from its conversion to the electricity. The power conversion system consists of a steam generator, turbine generator, and the support equipment, which convert the thermal energy into the electricity and supply it to the utility grid. The advantage of the central receiver or the heliostat field collector, there are 4 advantages. They collect the solar energy optically and transfer it to a single receiver, thus minimizing the thermal energy transport requirements. They typically achieve the concentration ratios of 300 to 1500 and so are highly efficient both in the collecting energy and in converting it to the electricity. They can conveniently store the thermal energy. They are quite large, generally more than 10 megawatt, and thus benefit from the economies of the scale. So these are all the solar thermal collectors. Previously in my previous lecture I discussed the non-concentrating solar thermal collectors, and in this lecture I discussed the concentrating solar thermal collectors. These are the references from where I take the notes and make the PPT. Thank you very much.